Hi friends, today let us see how to use or how to design a Chebyshev filter. A Chebyshev filter is a filter in which there are ripples in the pass band and no ripples in the stop band. So we'll always be designing a Chebyshev filter of type 1. So this design will be based on type 1 Chebyshev filter, in which there will be ripples in the pass band and no ripples in the stop band. Now let us read the question. The question says, design a low pass filter with 1 radian per second as its bandwidth, Chebyshev filter with following characteristics. So they are mentioning some filter bandwidth. They are mentioning the type that I wanted to design is the Chebyshev one, and they have given certain characteristics. The characteristics given are acceptable passband ripple of 2 dB, cutoff radian frequency of 1 radian per second, and stop band attenuation of 20 dB or greater, beyond 1.3 radians per second. Now let us start the solution. So what will be the flow of the solution? Just to recall, we will take the values of AP, AS, omega P. I'm extremely sorry, this is omega P, omega S, because all are analog characteristics. AP, AS, omega P, omega S. This will be my input. From this input, I will calculate epsilon, which is nothing but 10 raised to 0.1 AP minus 1 the whole raised to 1 by 2. From epsilon, I will calculate the order of the filter, which is n, which is given as greater than or equal to cosh inverse of 10 raised to 0.1 AS minus 1 divided by 10 raised to 0.1 AP minus 1 the whole raised to 1 by 2 divided by cosh inverse of omega P by omega S. So we will calculate the order. So first I will get the input 4 parameters, out of which I will calculate epsilon. From epsilon I will calculate my order, and after calculating the order and the epsilon, this has been calculated in this process. You can interchange it, that's not a problem, because epsilon is not viewed in terms of the order, so you can calculate interchangeably. After that, we are going to calculate the poles of the filter, but before going to the poles of the filter, we require a factor called beta, which is equal to under root of 1 plus epsilon square plus 1 divided by epsilon the whole raised to 1 by n. And beta is a factor required for the poles calculation, because the poles of the Chebyshev filter lies on an ellipse, and that ellipse is squeezed in the x-axis and elongated along y-axis. So what we will do is we will calculate the poles of the Butterworth filter first, and then we will squeeze them in the x-axis and we will elongate them on the y-axis by a certain factor, and that factor is beta. Then after calculating the value of beta, we will calculate small r, which is omega P into beta square minus 1 upon 2 beta, and we will then calculate capital R, which is equal to omega P into beta square plus 1 divided by 2 beta. After calculating both the R's, we will calculate theta k, which is pi by 2 plus 2k plus 1 by 2n whole multiplied by pi, and after calculating theta k, we will calculate the poles. and from poles are given by s of k, which is equal to rk, or we say xk plus jyk, and xk is equal to r cos theta k, and yk is equal to r sin theta k. Okay, so that will give you poles, and from poles I can calculate my h of s, and from h of s you can use any mapping technique to get h of n or h of z. Let us start. So from the given data of the problem, it has been asked us to find, the first step is to get the input data. So step 1, let us get the input data. For input data, I want AP, I want AS, I want omega P, I want omega S. Right. So in the problem, they have mentioned that design a low pass filter of 1 radian per second bandwidth. This factor is called as the cutoff frequency, and whenever there is no passband edge frequency specified in the problem, we take the cutoff frequency as the passband edge frequency. So my omega p frequency is 1 radians per second. Then we will go ahead and read the problem, and then they are saying that acceptable passband ripple is 2 dB. That means they have given that the maximum attenuation in the passband will be 2 dB. They have also suggested or said that the stop band attenuation of 20 dB or greater beyond 1.3 radian. So this value is stop band edge frequency, and after that the gain attenuation should be 20 dB or greater. So attenuation should be greater than or equal to 20 dB at frequencies 1.3 radians per second. So this is what the given 4 parameters are. That is step 1. Let us go to step 2. In step 2, we wanted to find epsilon. So epsilon is given as 10 raised to 0.1 AP minus 1 the whole raised to 1 by 2. Let us substitute the value of AP. This is 10 raised to 0.1 into AP is 2 minus 1 the whole raised to 1 by 2, and epsilon value is 0.765. This is my epsilon. Okay. Once you get the epsilon, let us go ahead and find the order of the filter. That is a step number 3. So step number 3 is nothing but the order of filter. So for the order of filter, I say n greater than or equal to cos inverse of 10 raised to 0.1 AS minus 1 divided by 10 raised to 0.1 AP minus 1 the whole raised to 1 by 2 divided by cos inverse of omega S by omega P. Okay, let us substitute the value. N will be then greater than equal to cos inverse of 10 raised to 0.1 AS is 20 dB, so 20 minus 1 divided by 10 raised to 0.1 into 2 minus 1 the whole raised to 1 by 2 divided by cos inverse of omega S is 1.3 radians and omega P is 1 radian. Okay, therefore N will be greater than equal to, this solution will come as 3.421. So I cannot design a filter of 3.421 factor. So you can design for 3, but what about 0.421, and you cannot skip that. If you skip 0.421 and take and design for 3, then your stop band edge frequency will go ahead again above 1.3 radians per second. But if the stop band frequency comes near a bit of the cutoff frequency, then it is always good. So the n factor is greater than equal to, that's why I will use n approximately equal to 4. So we will be considering as order of the filter to be 4. Now once the order is 4, that has been decided, let's go ahead to step 5. Once the order of the filter is known, now we can calculate the factor called beta, and beta is equal to root of 1 plus epsilon square, okay, plus 1 divided by epsilon the whole raised to 1 by n. Okay, so now my beta epsilon is, this is 1 plus 0.765 the whole square plus 1 divided by 0.765 the whole raised to 1 by 4. Okay, so that factor will come as 1.31. So that is what the factor of beta, 1.31. Using this beta, I am going to find small r and capital R. So step 6. Small r is equal to omega p into beta square minus 1 divided by 2 beta, which is altogether equal to omega p. Omega p is 1 radian into beta square is 1.31 the whole square minus 1 divided by 2 into 1.31. So R factor that you will get is 0.273. 0.273 is the R, small r factor. Capital R is given as omega p into beta square plus 1 divided by 2 beta. Okay, so if I put the value 1 into beta is 0.765 the whole square plus 1, no, beta is 1.31. I'm extremely sorry. This is epsilon value, this is not beta value, so it is epsilon value. Beta value is 1.31 square divided by 2 into 1.31. That factor is about 1.04. Always remember, capital R will be greater than 1, whereas small r will be less than 1. Once you have found R and you have found capital R, the next step is to get this is step 7, theta k, and theta k is given as pi by 2 plus, okay, 2k plus 1 times of pi divided by 2n. So now this is for k equals to 0, 1 to n minus 1, so it is 2, 3. So for theta 0 I will have pi by 2 plus 2k. So 2k is pi by, this will be 2 4s are 8, right, because n is equal to 4, that is the order of the filter of our case. That will come as 5 pi by 8, that is theta naught. As we know, theta is a function of odd integers of k, so every odd integer will reflect. So I can write theta 1, let's just solve theta 1, it will be pi by 2 plus, I will put k is equal to 1, so it will be 2 plus 1 divided by 2 into 4. So this is 2 into 4. So that will be pi by 2 into pi. So this will be pi by 2 plus 3 pi by 8. And that will be 7 pi by 8. This is theta 1. So as I got theta 1 and theta naught, you see that they are odd integers. So I can now say directly theta 2 will be equal to 9 pi by 8 and theta 3 will be equal to 11 pi by 8. Okay, so we have found all 4 theta factors. Let us go ahead and solve Now the poles of the, so now we are at step number 8. Let us find the poles of the transfer function. The pole of a transfer function s of k is given as x of k plus j y of k, where x of k is equal to, okay, small r cosine of theta k, and y of k is equal to capital R cos of, sorry, not cos, sine of theta k. Now what I will do, I will make k over here, which is going from 0, 1, 2, 3. Then I will write theta k over here, which is for 0 is pi by 5 pi by 8, this is 7 pi by 8, this is 9 pi by 8, and this is 11 pi by 8. Okay, then we write x of k value, we write y of k value. Okay, and combinedly I will write the value of s of k. Okay, so x of k for 5 by 2, if you put cos 5 pi by 8, you will get the value as minus 0.1. Okay, then for s of 1 you will get value as minus 0.25, then minus 0.25 and minus 0.1. Okay, next factors here, 0.96, then 0.4, then 0.4 and then 0.96. This is y. X s of k, which is x of k plus y of k, will give me minus 1 plus j 0.96 minus 0.25 plus j 0.4 minus 0.25 plus j 0.4 and minus this will be minus and minus, so this will be minus 0.1 minus j 0.96. Now how I know that this will be minus for sure is with the basic concept of the ellipse structure. Now we know that this is my ellipse, let's say, okay, which is having this as one axis and this as another axis, right? So if I place two of my poles over here, and they are going to portray over here also. So these poles are normally complex conjugate poles. So I know that the real part will also be negative and imaginary part will also go negative in the second two halves. Now let us go ahead. Now we have observed the poles. Let us combine the poles and make the transfer function. So step 9, we are now observing what is h of s. So h of s is equal to some constant k upon s minus s0 into s minus s1 into s minus s2 into s minus s3, right? So let us put s of 1, s of 2. Now where is s0, s1, s2, s3? This is for k is equal to 0, this will be s0. For k is equal to 1, this will be s1, 2, s2, 3, s3. Let us take it, substituted. So k upon s minus, okay, the first value is minus 0.1 plus j 0.96 into s minus, this is one of the term, next term s minus minus of 0.25 plus j 0.4, next term is s minus minus 0.25 minus j 0.4, and last term is s minus minus 0.96 minus j minus 0.1 minus 0.96. Okay, so this factor is minus 0.1 minus j 0.96, which is s of 4. or S of 3, the fourth pole. Now, to solve this, we need to check. See here, if I combine these two terms, then this is becoming S plus 0.25, here also S plus 0.25, when I take minus, this becomes minus, this becomes plus. Now let us combine them and write the transfer function k upon, I combine this first, so I get S minus 0.1 or it's S plus 0.1 minus J 0.96. Okay, and if you take this one, then it becomes S plus 0.1, this minus of minus becomes plus J 0.96. You can go for the next one, which is this 2. So, you will get S plus 0.25 minus J 0.4, which is this term. And lastly, you will have one more term with S plus 0.25 plus J 0.4. Okay. Now, let me write over here S plus 0.25 plus J 0.4. Now, you see this term as this is my A, this is my B. So, A minus B into A plus B will give me A square plus A square minus B square, but okay, let us say A square minus B square. So, now I will get equal to K upon A is my S plus 0.1 the whole square, correct? Now, B square is minus J 0.96 the whole square. This is one term. Second term is S plus 0.25 the whole square, okay, minus J 0.4 the whole square, right? Now, I will put it like this, K upon S plus 0.1 the whole square minus, now J square is minus 1. So, this becomes plus 0.96 square and this becomes S plus 0.25 plus 0.4 square. Okay, and the factors or the expansion will actually come up to, if you open the brackets and if you solve the whole thing, it will be S raised to 4 plus 0.7 S cube plus 1.25 S square plus 0.51 S plus 0.12325. So, this is my transfer function h of S if you wanted to open it up. Now, what is this constant K? Now, K is equal to B naught upon root of 1 plus epsilon square for n to be even. If n is even, then K is equal to B naught upon root of 1 plus epsilon square, and B naught we considered to be a constant term in the denominator. Okay. So, let us say my K is equal to, let us take B naught as 1 divided by root of 1 plus epsilon is 765 the whole square under the root. Therefore, my K will be somewhere around 0.16. Therefore, the transfer function h of S, that is a design, is 0.16 divided by S raised to 4 plus 0.7 S cube plus 1.25 S square plus 0.51 S plus 0.12325. So, this is a analog transfer function of the required filter which has been asked in the question. So, this is how we need to design a Chebyshev filter. In all, there are totally roughly 10 steps. So, this is how it is more mathematical, and you need to do a huge cumbersome calculations when you are solving a Chebyshev filter. Thank you.